Welcome to The Explainer. Today we're unpacking the invisible architecture that powers, well, the modern internet. Every single time you type a few words into a search bar, whether you're hunting for a very specific document on Google, a new job on LinkedIn, or just a pair of shoes on Amazon, you're triggering one of the most complex, high-stakes engineering marvels on the planet. We're going to follow this fascinating query journey inside a modern AI search engine, step by step, to see exactly how these systems figure out what you want, almost before you even know it yourself. Okay, let's dive right into this. To truly appreciate the sheer scale of this system, you first have to wrap your head around the ruthless latency budget it operates under. From the second you hit enter, a modern search engine has to complete its entire end-to-end operation in under 300 milliseconds. We're talking about the P99 latency here, which means 99% of all searches must be completed in the literal blink of an eye. And the actual ranking part of that process? It only gets about 50 milliseconds of that pie.
Now contrast that tiny 300 millisecond time window with the staggering scale of a typical modern corpus, 100 billion documents. I mean, for a massive vertical like product or people search, you might be looking at hundreds of millions of items. And these indexes aren't just sitting there. They're being continuously updated in near real time just to keep the content fresh.
So here is the million-dollar question. How do we actually search 100 billion things in just 300 milliseconds? Think about that. How does an AI system instantaneously sort through an absolute ocean of data, understand exactly what you mean, and hand-deliver the perfect results? Those are the impossible stakes of this engineering problem, and today we're going under the hood to see exactly how they pull it off.
Here's our roadmap for the explainer. We'll start with the anatomy of a search, move to decoding the user query, and then the great retrieval. From there, we hit the ranking gauntlet, measuring search success, and we'll wrap up with trade-offs and system evolution.
All right, Section 1, Anatomy of a Search, the high-level architecture. Let's get a bird's-eye view of how this all works. And this brilliantly illustrates the whole life cycle of a search request. Notice how it starts way over on the left with the user's query, passes through query understanding, moves right into retrieval, and then hits the learning to rank models and neural re-rankers before finally assembling the search engine results page, or SERP. It's a beautifully constructed pipeline. It takes an incredibly broad universe of data and systematically, almost ruthlessly, narrows it down. Which brings us to this really defining concept. Search is a query-driven funnel. You see, unlike a recommendation feed where you just kind of scroll passively, search requires a specific intent. We start super wide at the top of the funnel to maximize our recall, basically making sure we don't accidentally miss anything relevant. But as we move down that funnel, the models become heavier, they get smarter, and they are much more computationally expensive, narrowing everything down to maximize precision without blowing our strict compute budget. Moving on to Section 2, Decoding the user query, making sense of this search. This is where the system first collides with our messy human input. Let's be honest, human beings type terribly. We make typos, we use weird abbreviations, our phrasing is super ambiguous. Query understanding is what breaks this messy text down into a nice, clean checklist. First, it normalizes the text. Next, it spell corrects, right? We've all had that moment where we completely mangle a spelling and the search engine instantly knows what we meant anyway. Then it classifies the intent. Like, is this user looking to buy a new laptop or just read an article about one? Finally, it extracts key entities, things like specific locations or brands. Nailing this query understanding phase is absolutely vital. If you fail to extract the right intent or the correct entities right at the starting line, the rest of your brilliant, highly complex ranking models are essentially running blind. Query understanding determines your baseline recall quality before any of those heavy ranking models even get a chance to run. Section 3, the great retrieval. Casting the net. We've got to pull thousands of relevant candidates out of those 100 billion documents instantly. To pull this off successfully, modern systems actually use a hybrid fusion of two totally different retrieval techniques. On one hand, we've got classic lexical retrieval. Think of this as your old-school exact keyword matching over an inverted index, using algorithms like BM25, super fast, very precise. But on the other hand, we have semantic retrieval. This uses dense vector embeddings and approximate nearest neighbors to find documents based on their underlying meaning, rather than just relying on exact keyword matches. Fusing these two approaches together, that gives us the ultimate combo of exact match precision and deep semantic recall.
Section 4, the ranking gauntlet, the deep learning crucible. We have our candidate pool. Now things are going to get computationally heavy.
Okay, to rank these thousands of candidates, we run headfirst into a massive cost versus accuracy trade-off. Deep learning models, they are incredibly accurate, but they are way too slow to score thousands of documents in 50 milliseconds. The ingenious solution here is a cascade method. Basically, we use cheaper, faster models to score the thousands of candidates first, and then we spend our heavy, deep computing power only on re-ranking the top few dozen results, because let's face it, that's where it actually matters to the user.
Now, what's really interesting about this is the logic of the cascade itself. We don't just blindly use the smartest model for everything. We start with BM25, which gives us decent medium quality with very low latency. Then, we pass those narrowed-down results to an industry workhorse called LambdaMart, which is a learning-to-rank model that pushes the quality way up while keeping the latency low. Finally, for just the absolute top tier of results, we unleash a neural cross-encoder. It provides the absolute highest possible quality for deep query document interaction, but its latency is super high, so we have to use it incredibly sparingly.
Section 5. Measuring search success. The feedback loop. How does this system actually know if it's doing a good job?
The gold standard for measuring offline search relevance is this intimidating acronym, NDCG, or Normalized Discounted Cumulative Gain. But honestly, this metric just proves mathematically what we all know intuitively. The number 1 spot matters infinitely more than the number 10 spot. It harshly penalizes the system if highly relevant documents are buried lower down the page, and it rewards the system massively for putting exactly what you want right at the very top.
But to actually train the model for high NDCG, we run into a major data tension. On one side, we have implicit user clicks. These are highly abundant, very scalable, but they are heavily biased because, let's be real, users blindly trust the top results and usually just click the first thing they see. On the flip side, we have unbiased, graded relevance from actual human evaluators. Fantastic quality, but incredibly expensive and sparse. So production models survive by blending the two together, using debiased clicks for sheer scale and human judgments for precise calibration.
Here is a totally awesome insider engineering secret for testing these models out in the wild. Instead of your standard A/B testing, where Group A gets one algorithm and Group B gets another, search engineers use a technique called interleaving. They literally zip the results from two different rankers together into one single list, kind of like a zipper, and show it to the user. Whichever ranker's results get clicked more is the winner. It's a wildly more sensitive testing method that detects ranking differences using orders of magnitude less traffic. Pretty brilliant, right?
Section 6. Trade-offs and system evolution. The balancing act.
Designing a system that searches 100 billion documents in a third of a second means system designers are constantly walking a tightrope. It's a massive balancing act. They have to weigh the pure accuracy of massive neural networks against that strict 300 millisecond latency budget. They've got to fuse the precision of lexical matches with the broad recall of semantic meaning. They try to offer you personalized search results while fiercely guarding your privacy. And they have to balance the rock-solid stability of the index against the constant, urgent need to inject fresh, newly published content. And you know, one of the biggest trade-offs they face is the so-called cold start problem. Because user click features absolutely dominate the ranking signals, it creates this intense rich-get-richer loop. Popular documents sitting at the top get all the clicks so they stay at the top forever. If the system didn't deliberately inject a small budget of randomness, a little bit of exploration, brand new, amazing content would never get a single click and would just be buried indefinitely. Semantic features and this slight randomization ensure that new content actually gets a fair chance to be discovered.
So we've seen exactly how the traditional search funnel works. But as these systems evolve with advanced multi-vector retrieval and deep learning, we've got to ask, how will LLMs and generative AI answer layers eventually shatter this traditional query funnel forever? Think about it. If a system can just generate the exact perfect answer directly from a grounded knowledge graph, will we even need to rank 10 blue links anymore? It is a fascinating question, and it's literally what the entire industry is racing to solve right now. Thanks for joining us on this deep dive, and keep your curiosity peaked for what's coming next.